Hi, my name is Adele, and I work on data science team partnering with Treasury. So my talk today will be slightly different from your typical data science talk because I will talk about how to apply financial models, such as financial portfolio model, to tech industry. Okay, so you may have heard about Markowitz, who is a famous American economist who also won Nobel Prize. So Harry Markowitz is most famous for his work, which is called modern portfolio theory. Without going into too much detail, basically what it says that if you have an investment portfolio, you want to have investments with the highest return and the lowest risk. So this is something which he calls efficient frontier, that line. You want all your investments to be as close to that line as possible. Now, let's go back to tech industry for a second. I'm going to play a lot of quizzes with you today, so be prepared. The first question is, what is the mean target for an early stage company? Any takers? Yes, revenue growth. Okay. What about as the company matures? Related to revenue, but kind of more tailored. Okay, that is margin, because you want long-term sustainability, and revenue minus costs and losses is margin. Now, what is your ultimate target for long-term profitability? Okay, that was a trick question because I'm going to give you an answer at the end of this talk. Okay, so now let's think about how we can apply this efficient frontier to a tech industry. What do you think the axis become? Remember, this was return. What it becomes? Margin. Because we pretend that all these dots are not investments, these are our users. So how much return each user generates is how much margin we make. And what is our risk? Losses, because we have losses from the user. Now, every business has risks. How can tech company have losses? It can be user defaulting, fraudster attack, security breach, regulatory fine, lots of other reasons. But for the purpose of today, we'll only focus on credit losses. Okay, what should we do with losses? Another multiple choice question. A, mitigate completely. B, let them be. C, take smart risks. Okay, well, let's take a look. So why is mitigating completely bad? Because how can we mitigate losses and risk? By putting a lot of controls in place. We introduce user friction, and then good users run away. Let them be is not good. We'll just burn cash. So take smart risk. Now, it sounds easy. How do we do that in practice? So here is another quiz for you. I'm going to tell you about two hypothetical users, user A and user B, and you'll tell me which one you think is better for Stripe. Okay, user A is a ride-sharing company. So cardholder, such as yourselves, pay after taking the ride. And then let's say user defaulted. You will not file a dispute because you already took the ride. What is there to dispute about? So there is no credit loss to Stripe. Now, user B is a hypothetical artisan chocolate weekly subscription company. So you pay weekly subscription fee, and then the chocolate ships to you after 3 days. Now, let's say the factory had a fire, user defaulted, unfortunately, and then all of you will file disputes, and then Stripe has credit loss. That's how credit losses arrive at Stripe. Now, which user is better? Okay, people's, I can see A. No? Okay. So that was a trick question again, because I made this example such that both users are equally attractive to Stripe. Now, you may wonder, how is that possible? One of them has losses and another one doesn't. The answer is modern portfolio theory. Now, remember our axis for this efficient frontier, we have margin and losses. Let's plot these users on this graph. Chocolate subscription company has a lot of losses, but they also pay high price because they're a small user. So we get high margin from them. And the ride-sharing user has no losses, but because they're such a large company, they were able to negotiate a big discount. So we get lower margin from them. So on a net basis, they're both the same. Now, if we want to apply this framework to the whole, to all of our users will have to model losses for all users. And the way we do it at Stripe is we break losses into two components. The first one is probability of default, so how likely do we think that the user will default? And the second one is exposure at default, which means if the user default, how much money we will lose. And then we model losses as probability of default times exposure at default. Okay, now you're probably thinking, thanks God there is some machine learning graph because this is a data science talk. So we implemented 7 different models to model exposure. And the way we model exposure is by modeling this loss curve. So basically, you look at time prior to default and what percentage of charges will be lost at each point in time. Now, we implemented 7 different models ranging from simple statistical distributions and linear regressions to mixed effect models and random forest. And we found that random forest performs the best. The green line is the actual and the random forest is the closest to the actual. We also evaluated precision for ranking merchants by predicting which will be the largest losses. And here we found that random forest also performs the best. So we went with this model and implemented it into production. When it comes to modeling probability to default, we don't have a lot of internal data, and this is one of the very few cases where we are very happy to say that we don't have a lot of internal data because we don't have a lot of users defaulting. So what we did is we took external data and we adjusted it to account for some of our user specifics, and then we assigned a probability to default to each user based on their industry, size, and some other factors. Now let's go back to our efficient frontier. And if you are able to forecast losses, you are able to plot every user on this graph in terms of how much margin they'll generate and how much losses they're likely to have. And then you can very quickly see that we also have efficient frontier for our users. And then if you have a user like that blood dot out there, which doesn't look great, then there are a number of things you can do. 1 is to increase the price, and 2 is to reduce the loss, reduce the risk, actually. Okay, so the answer to our question is the ultimate target for a long-term profitability is return on risk ratio. And at Stripe, we're now moving to implement this framework for our existing users as well as to our prospect users. Okay, thank you for your time. And actually, if you have any questions, we're going to take 1 question per talk. No questions?
I'm curious about the probability of default comes from external data. Like, does it require to purchase it or partnership? Because it's like quite sensitive private data.
Oh, so we actually use it by industry. So we used open source data such as US Bureau of Census. There is a PayNet Small Business Default Index. And there is Moody's as well. There is some public data which is available. But we also plan to buy some data on specific companies. And I think we already started doing that. Okay. So I'm going to pass it to the next speaker, Dara.
Thank you, Adele. My name is Dara. I work here at Stripe with the finance, sales, and operation teams as a data scientist. I'm excited today to give you a little taste of some of the forecasting methods and tools that we use, as well as hopefully inspire you to think about forecasting and how you might apply some of these models in your own work. So before I go into this, you might ask me, why would one forecast at all? First of all, you get to predict the future, and that's just cool in itself. Second of all, forecasting models are highly business relevant. They aren't always brought up in academic contexts where the focus tends to be on classification and regression models. But when it comes to businesses, almost everything is a time series. And so understanding time series modeling and how to apply it in your work is going to provide a number of highly business relevant solutions. Third, forecasting models are statistically interesting in themselves. Learning about them is not only fun from a learning new models point of view, but also the way that we choose forecasting models and evaluate them will really benefit how you think about modeling in general and can apply that to other models in your work. So this is some data that's freely available in R. I'm just going to use it as an example. It's the number of air passengers internationally in thousands from 1949 to 1960. And this is a nice time series that can illustrate a number of modeling considerations that you want to keep in mind when you're setting up a new forecasting problem. So the first thing to think about is the trend in your data. Is it linear? Is it exponential? Is it somewhere in between? Or do you have more of a stable or even a decreasing trend? Understanding this aspect of your data will help you make a decision about the type of model to use. Secondly, do you have any seasonality in your data? So this could be weekly or monthly or daily seasonality, or even sub-daily seasonality like hourly or minutely. Third, what is the length of history that you have in order to make a prediction? And fourth, how long of a prediction do you want to make into the future? Also important to consider whether you want to make first, autocorrelation. So how related are 2 points in time? In other words, how does one point in the past predict the future? Finally, do you want to make an uncertainty interval prediction when you're giving your forecast? And then not shown on the chart are external factors. So are there other sort of covariates in addition to your time series that you want to be able to include in your model? Or are you going to just be modeling on the time series itself? So these are a subset of forecasting models that we use or experiment with here at Stripe. So the three main buckets here are first regression models. So these are things like linear regression or Facebook's tool, which is called Profit, which is a piecewise regression model. These are great if you have those external factors that I described that you want to include in your model. Oops. And then classical forecasting models like ARIMA, that's autoregressive integrated moving average, and exponential smoothing can work really well if you want to explicitly model seasonality or if you have a lot of autocorrelation in your data. And then the deep learning models over here, like recurrent neural networks, RNNs, or long short-term memory networks, which are a subset of RNNs, are really good if you have a lot of data as well as a lot of external factors and maybe unpredictable patterns that you want to be able to model. Recently, people have also been using convolutional neural networks, or CNNs, especially a variant called dilated CNNs. And these have been working pretty well for modeling certain types of seasonality as well. So important to be open in your choice of neural network if you go that direction. So those are all sort of building blocks that we use. When we are approaching a forecasting problem at Stripe, we want all those tools at our disposal, and we want to be able to combine and extract them in new ways. Because we are a payments company and we want to forecast, for example, our payments processing volume. So how much volume is actually flowing through Stripe at any given time. Now, we're interested in this for Stripe overall, but we're also interested in many different segments. So, for example, how much volume do we have in Europe? How much in North America? How much in Asia? And within each of those buckets, how much is from small businesses, medium businesses, or large businesses? We want to be able to use different models to predict those individual segments, but we also want the forecast to add up to a coherent whole. So we use a cool optimal reconciliation method that I'll describe in detail in a moment to be able to do that. Essentially, it lets us take any of those forecasting models that I described and use them as building blocks to forecast each of our segments. And then we can use the reconciliation to tweak them so that they add up to the whole. So this is how we do it. It's going to be a little bit of math. So we start with we're ending up with our reconciled forecast here. So this is the end goal. We start with our original forecast that we got from whichever models we used for our different segments. There's two matrices that are going to help us make this prediction. The first one is S, which is a binary summing matrix. So this dictates how the hierarchy is aggregated. So this is essentially just ones and zeros describing how the hierarchy is set up. It's determined ahead of time. The one that we want to learn is the G matrix. This is the combination matrix. And this is going to have the coefficients that describe exactly how we can extract and combine the individual models together. To give you a little more intuition about this, we can think about our reconciled forecast using this notation. So here is the total forecast, the Y tilde T. You could think of these as the sort of top level cuts in the forecast. So this might be Europe and North America. And then these would be sort of the second level. So Europe small businesses, Europe medium businesses, Europe large businesses, etc. This is our summing matrix that we use. And so you can see we use it to dictate how we add up the bottom level of the hierarchy into the top. Over here is our bottom level forecast means. These are unknown to start with, but you can see we're using our notation here to indicate that this would be the very bottom level of the hierarchy. So to expand that out into G and Y hat H, so Y hat H is the same as Y tilde H in that, but it's our original forecast, but the notation is very similar. And then we have our G matrix. So this is the one that we want to estimate. This is the unknown matrix. And estimating this is going to allow us to do our reconciliation. There are a number of methods you can use to do this estimation. Least squares is a good one to start with, but we also use methods that allow us to weight the reconciliation by the variance of the individual forecasts. So we've found this to be a pretty useful tool, and thus we've implemented it in an R package, which we call Teller, loosely named for Edward Teller, who famously predicted climate change before it happened way back in 1959. So we've implemented the reconciliation method I described, as well as a number of the building blocks that I described. We also have methods for bootstrapping and backtesting implemented in Teller as well. And because I could forecast that I will get this question, we don't have plans to open source this anytime soon, but we do have plans to keep hiring data scientists. So feel free to come chat with me if any of this sounds fun. So we have used Teller and a number of these methods to forecast not only financial metrics here, but a number of other metrics. So we forecast operational metrics like risk reviews and our support volume, and the number of other things that we're forecasting is growing every day. This works fairly well for our business model. We routinely achieve 3 to 5% forecast accuracy, sometimes as low as 1%. And we continue to sort of improve and evaluate these methods all the time. So with that, I'm happy to take any questions. What do we use the forecast for? Yeah, so on the financial side, we might use them to set our budget yearly. So we forecast our processing volume, and that can determine a number of things downstream. And for things that are more operational, like support volume, we use that to determine our staffing. So how many support agents should we have for any given week? So number of use cases. Okay, here's Elaine.
Thank you. All right, good night, everyone. It's so great to have you all here today. My name is Elaine, and I'm part of the growth data science team here at Stripe. My team mostly partners with growth product and marketing team, focusing on user onboarding problems. So we're trying to reduce the friction users experience when they're onboarding to Stripe, and also educate them about the products that Stripe offers. Because product adoption is a key part of our core metrics, I'm going to talk today about a concept called Jobs Done framework, how we have been using it to design our metrics around product adoption, and how have we ultimately used it to prove that more jobs done is correlated with higher margin and lower churn. So let's get started. What is jobs done? It was a concept that was brought up by this Harvard Business School professor called Clayton Christensen. He's also written a few of my favorite books, such as like How You Measure Your Life and stuff like that. So one of my favorite authors, I would highly recommend you to find his books. So he brought it up in his recent book called Competing Against Luck, which is basically saying customers don't buy your products or services. They hire them to do a specific job. And what this actually means is instead of tracking like whether users are buying or being active on your products, you should really like drill down into like what are they really trying to hire your product for. And there's one classic example around milkshakes. So researchers have done like milkshake research for a specific fast food chain company, trying to figure out like why would people buy the milkshakes. And they found out that a lot of the buyers for the milkshakes are actually people who have long and boring commutes. So the job they're hiring the milkshake to do is ultimately trying to make their commute a little bit more fun. And with that job in mind, the milkshake producers can design their milkshakes to make it even more fun to drink. And with that, I think they actually like drive the sales up by like 7x according to the book. And there has been a few like famous adoption of this concept in the tech industry as well. I think one of them is actually described by the Netflix CEO. I have some Netflix friends over there who describes that the actual job that Netflix as a company does is to help people unwind at night. And in that sense, it actually competes with stuff such as sleep and playing video games and reading a good book instead of like classic competition like you might think about like HBO or Amazon. So back to Stripe, how this job sensing has been useful for Stripe. As a data science team helping with the growth team, we face mostly two questions. First of all, are we really driving more product adoptions? That needs a Stripe-wide company metric around product adoption on Stripe. And secondly, what does more product adoption bring to Stripe? Like, why does it matter for Stripe? So, like, in order to do that, we need to really create a product adoption metric. And our old way of thinking about this is just to track number of active users on each product, which has been a problem for Stripe, mostly because so many of our products are so complicated. I'll take one of them as an example, which is a dashboarding tool that we have built. You can imagine it as a user interface on top of all the transactions. This main interface looks like a dashboard with a lot of graphs. And if you click into, say, the payments tab, it's like you will enter this SQL table-like view with like all the transactions for each payment. And if you click into like other tabs, it introduce you to the features of the products and all that. So you can imagine user can use the dashboard to do so many different things. But historically, the team has been tracking number of dashboard active users. And you can imagine it's not super useful for the team, mostly because, okay, users are active on dashboard, so what, right? Like maybe there are use cases that don't require that much activeness on the dashboards. And also like dashboard is this monitoring tool. How can you combine usage of this product with some of other software products that we also provide, such as the product that allows you to charge your like subscription users? So those are the problems that we're facing and how we're using JobStand to solve it. We did a clustering analysis purely based on user activity signal on dashboards. We didn't take into any demographic features with this clustering analysis. And we ended up with a few like main clusters of users. Like there's one cluster that's very high in using dashboard in checking their business performance, a cluster of users who are using it mostly for charge operations, like refund their customers, invoice their customers, etc. And you can imagine those users are using dashboard in very different way, and you should really develop different features for those users to optimize their use cases. So because you guys are mostly data scientists, I'm going to talk a little bit more about the clustering like practice that we have done. So we basically build this model based on 30 plus features. And we started with the classic album method to estimate rough number of clusters. And then we use principal component analysis to reduce dimension and visualize the clusters and to see does it make sense or not. In order to do it, the HyperTools package actually came in handy. And ultimately we used the box plots to find what are the features that really distinguished the different clusters from each other so that we can like profiling them basically. And this solves a problem for us with like clear use cases in mind. We can actually track our metrics around those use cases. We can design our products to optimize the use cases. And also this can be combined with other use cases like other jobs that users are using with other softwares, because Stripe as a company, we just want to make sure that users are doing more jobs through us so that they're more sticky with Stripe. And we have worked with the product team to come with jobs for every individual product within Stripe, and we built a core data set which tracks whether a merchant is active using a job on a specific day. And how this has been useful for us is it answers to two questions. First of all, how good we are at driving product adoption. You can just imagine a metric which tracks the average number of jobs per merchant over time, and we can see if it's trending up. And we can break it down also by key segments to see like what are the main segments that's driving up the metric, and also by cohort to see if we're educating our new users better over time. And we also used it to prove the value of higher stickiness, aka more jobs done. And we proved that like more jobs done is actually correlated with higher churn, higher margin and lower churn rates based on the graphs. And we always like conceptually know about it. And it's great to actually have a sense on like what is the added value of more jobs. So we also use regression analysis, taking into more factors that might affect churn and margin in addition to number of jobs, which draw the same conclusion. The impact on higher stickiness is still pretty significant. And we're also like doing the regression analysis on a per job basis, like from which you can basically see which job is contributing the most in driving higher margin and lower churn. So we share that with our go-to-market team so that they can use it to design their cross-sell and upsell strategy. Thank you very much, everyone. And I can take one question, I guess. Yes.
Okay, so I was curious, like you talked about more engaged users. Like,
Yeah.
so did you actually look at your less engaged users, and how do you define what more engaged?
So more engaged is basically they're doing more jobs through Stripe. So they have like more use cases that they're using Stripe to solve. And less engaged is probably like they're only processing payments through Stripe without doing like anything else.
So before you actually did the jobs to be done, like so remember when you showed the clustering, so you actually figured out what jobs they were doing. So
Yes.
at that point itself, you could see that the less engaged people were just doing less things.
Oh, yes. So we actually broke down the less engaged clusters as well, and then found like maybe like a little bit more jobs than what we're showing here. Thank you. I can take more questions offline if you want to chat. Thank you so much. I'll introduce Lakshmi.
Sorry, I was trying to figure out if there's a laser pointer on this thing, but there's not. It'll be okay. Cool. All right. Hi, my name is Lakshmi, and I work with the engineering team that builds Stripe's core credit card processing infrastructure. Today, I'm going to share some recent work that I did to find and measure heterogeneous causal effects in credit card transaction experiments. First, I'll briefly introduce how the credit card transaction flow works. Next, I'll talk through a challenge that we have faced in detecting heterogeneous effects in our data. And I'll describe a methodology that we used to address this challenge. And finally, I'll share some results from a recent experiment we did where we applied this methodology at Stripe. But first, heterogeneous causal effects is a little bit of a mouthful to describe a pretty simple problem. So imagine that you are a plant biologist and you run a randomized experiment to test whether plant growth is accelerated by applying fertilizer. You find that plants treated with fertilizer grow faster, but the fertilizer affects the growth of some plants differently than others. And this is what we're referring to as heterogeneous causal effects, cases where the effect of an experiment differs in subpopulations that we're looking at. Okay, so how is this relevant to Stripe? One of the core jobs that Stripe does is to process credit card transactions for internet businesses. So the way Stripe does this is we have a request to charge, we pass it to a card network like Visa or MasterCard, they pass it on to an issuing bank, the bank that issued the credit card. And then the issuing bank says whether or not the charge can be authorized, and we get that response back from the card network. But one thing that's really important in this flow to think about in terms of the business case of this flow is that anytime a legitimate charge is declined by the issuing bank, our merchants are losing revenue. And because that's so critical for our business, we're really strongly incentivized to boost authorization rates like as high as we possibly can so that revenue makes it to our merchants.
And one of the things that we do to optimize our authorization rates is to run experiments on the messages that we send to the issuing banks. And when we run these experiments, we measure the overall impact on authorization rates, but we're also really interested in identifying subsets of charges that might have differential performance. So for example, if an experiment increased the authorization rate for one bank, but decreased it for another, we would need to know that so we could optimize our messaging infrastructure on a per bank basis. So if we knew that treatment effects only varied by issuing bank, we could slice our data by bank, do some corrected statistical tests, and be on our way. But this actually becomes much more challenging when the variable space that we might want to explore to find pockets of differential effects becomes large and complicated, which is the case for our authorization experiments. And to give a flavor of this, on the left is a list of some of our card features that we have that we might want to slice by. And for an example, you can see that in our data, we can have 10,000 or more issuing banks. And then we also have a set of transaction features which might interact with our card level features. And so given the size and complexity of this data set, how do we find pockets of differential experiment performance so we can optimize? To approach this, we tried out a methodology called, from Athey and Ibben's 2016 paper, Recursive Partitioning for Heterogeneous Causal Effects. And this methodology is comprised of two main steps. First, we use decision trees to find groups of charges with similar treatment effects. Second, we use a holdout data set to estimate the effect that the treatment had on those two groups. The advantage of this methodology is that it allows us to algorithmically group subsets of charges with differential treatment effects, even if we have no prior knowledge about what variables we should use in creating those groups. And so in the next couple slides, I'll talk through how this methodology works in a little bit more detail. So first step, split your data into your training data set and your estimation or holdout data set. We're going to use the training data to train decision trees to predict the difference in authorization rate between the treatment and the control. So a conventional regression tree would do its splits to minimize the prediction error on the outcome variable. But in contrast, this algorithm to identify heterogeneous effects uses a decision tree algorithm that'll choose splits to maximize the magnitude of treatment effect. So that's a lot. Let's take a simple example. So say we have a data set that has two features, bank and transaction amount. The way our algorithm works, we would first, at the top of the tree, we would split on the variable that gave us the highest magnitude highest magnitude treatment effects in each of the nodes coming off of the split. So in this case, we would split on bank first. As the algorithm continues, it'll traverse down the tree, making these splits, and it'll actually, without any optimization, it'll do so until it doesn't have any more variables to split on. But to constrain overfitting in this case, we use cross-validation within that training data set to choose the hyperparameters that'll control tree depth. And so we'll select the hyperparameters that give us the tree that allows us to most accurately predict treatment effect. So in this case, because we see these two leaves here have pretty similar magnitude treatment effects, when we did this hyperparameter selection for tuning, we would probably end up with suggested clusters with only 3 nodes. And so you see that one of the groups would probably be bank number 2. The second group would be bank number 1 charges that are less than $50. And then the third group would be bank number 1 charges that are greater than $50. And then once we've identified these subsets that we want to split our data into, we can go back to our holdout or estimation data and do the treatment effect estimation and significance testing using our holdback data. So next, I want to move on. So with that overview of how the methodology works, I want to share some results from a real implementation that we did here at Stripe. So we used this method to analyze data from an experiment testing a new messaging feature that Visa recently introduced in their authorization messages. When we ran this algorithm on a data set of about 10 million charges, we ended up with a reasonably deep tree that suggested that we split our data into approximately 50 subsets. When we pulled in the holdback or estimation data, we found that 14 of those subsets had significant treatment effects. And then digging into what was determining where these subsets were split out gave us some pretty interesting insights. We found one low-volume international bank where the treatment had an extremely positive effect and charges actually couldn't get authorized without the treatment. Conversely, although the treatment had a positive effect overall, we also identified banks where it had an extreme negative effect. And then finally, we found interesting cases where the magnitude of the treatment effect actually varied within an issuing bank depending on the other properties of the charge. For example, in one case, we found that the treatment had a strong positive effect on charges where the zip code was not sent, but no effect on charges that were sent with a zip code. So we ended up using these results in a couple ways. For banks that showed an extreme negative effect, we communicated these performance issues to Visa so they could work with those banks to get into compliance with the new messaging infrastructure. Additionally, understanding where most of the positive lift was coming from informed how we incorporated this new messaging feature into our authorization optimization infrastructure. So specifically, seeing which variables the decision tree split on allowed us to incorporate, to make sure that when we were optimizing, we did it at the appropriate level of detail. Since some of the pockets of differential performance came from an interaction between bank and transaction level features. So in summary, we found that the recursive partitioning for heterogeneous causal effects methodology was a useful tool for extracting insights from large data sets. It allowed us to improve our authorization rate optimization infrastructure and to automate analyses that we had previously done in a time-consuming, ad hoc, and manual way. So because we found this methodology valuable, we created some internal documentation of all the implementation tips and gotchas, and also pointers to help for functions that we wrote along the way. So this is now part of our standard experiment toolkit at Stripe. Thanks very much for listening, and it looks like we have time for one question. Yes?
After you got the splits, how do you infer? How do you get to the point where you understand why were they split accordingly?
Yeah. So the first part of the question, how do you do inference? So essentially, we just took the holdback data. So we took the holdback data, we split it into the groups suggested by the tree, and then we ran multiple comparison adjusted Fisher's exact tests to see where the significant treatment effects were. And then in order to build intuition around what the tree is actually doing, which is one of the most important parts, we just basically had functions that sort of traverse back up the tree and identify all the split points. And so then you can say, okay, for each of these leaves or each of these final groups, I know exactly which variables it's split on. So that part actually, so you can return an output table that has the final treatment control effect and then also all the different splits as well.
So basically, basis the split variable which was used for splitting and where it was, so you could infer.
Exactly, yeah. Thanks.
Cool. Hi, I'm Molly. I'm a software engineer on the data libraries and pipelines team here at Stripe. One of the things which we do with our team is we write libraries on top of Spark, which other teams use to build their own pipelines. So as part of this talk, I'm going to talk about data skews. How do you handle data skews using sketch joins, and a bit about sketch joins themselves. So a very brief primer into Spark. So Spark, as you know, is a distributed job framework. It basically processes big data, which is divided into various partitions. So this is horizontal scaling, where you can send these partitions into different machines to be processed. So what is skewed data? Example, this is an example of a join. say you have a data set called countries, which is a mapping between the country code and the name of the country. And I have a list of transactions, which is, again, country code and the transactions which happened. And eventually, I want to get that data set on the right after the join, which is a transaction amount and the complete country name. Now, the way Spark would do the join is that it would actually send all the entries belonging to one single join key into one partition. And as you can see, for this country code, which is US, there are more number of entries compared to some other keys, which means is that there would be no more number of entries sent, that all the entries of the US would be sent to one single partition. So this is obviously a very simple join, but imagine if you're sending, say, millions of records into one partition. So that is what we call is a skewed data, and that can mean, and skewed data can cause your job to fail or for it to like run very slowly. So how do we handle skewed data? So going back to the same example again, imagine that apart from the country code, we also had states. Now, since we know that a state would belong to the same country, we can actually use the country name and the state as the combined join key, and that would give us the same output. But here, if you see, the records of the US are right now getting divided into different partitions. So that means one partition is not overloaded anymore. So we have handled the skew so the job would run properly. Now, for example, now let's imagine we don't have that column anymore. We don't have a different column to kind of like join with to handle our skew. So what do we do? So in this example, I just took some numbers. So let's say I just chose that I'll actually divide the ones in US into 4 groups. So I just randomly assigned them, and same with the other 2 entries as well. So eventually I want, again, to get the same join output. So what should be the columns here for countries? Now, since I have four entries here, and my join key is going to be the country code and an integer number which I've selected, that means there should be at least that many entries for that particular join key in the countries data set, right? So that means for 4 US entries here, I need at least 4 US entries there as well. So which would give me the final join, and I don't have any skew in that data. Now, this is a very small data set, so I could like say, okay, fine, I'll just assign the numbers. But how do you do it when it's a very large data set? Just looking at that, just looking at this, you can probably imagine that it should be proportional to the count of the key. Like the number of groups you're splitting into should be proportional to the counts of the key. So which means we need to kind of like get that how these keys are distributed in the larger data set. So obviously, I can probably go do a scan of the larger data set and find out the keys and the counts and keep them in a map somewhere. But imagine if you have, say, billions of rows. That would take a lot of time first, and that would take a lot of space as well. So how do we find out the counts? So we are going to talk about data sketches, specifically about count-min sketch. So it is a probabilistic data structure which is backed by a very constant tiny footprint, and which can give you approximate counts of the keys which it has seen. So it is backed by a table, and you can choose the dimensions of the table. So if you want like better accuracy of the counts, you increase the size of the table it is backed by. You can imagine it is very similar to a hash table. So hash table has one hash function. Count-min sketch, you can choose the number of hash functions. It can be multiple. So what would a count-min sketch look like, for example? So this would be a normal map with counts if you just take the keys and the counts. But for count-min sketch, I chose 3 hash functions and 4 different rows. So say for hash function 1, US map to 1. So I incremented the cell over there in the first. For the hash function 2, US, the hash value was 2. So I incremented the value in the second row. And similarly for hash function 3, so again, the US map to 2 again. So I incremented the value there. So whenever you see a key, you take the 3 different hashes and you incremented the corresponding value in the table. Similarly for Singapore, you can see it mapped to 3, 2, and 4 in each respective hashing functions. And when you want to get the count of the key back, you again like hash it. You know that US had mapped to 1, 2, and 2. So, and we get the corresponding numbers. That means this, which are 4, 5, and 5. And you take the minimum of that, which is why it's called like count min sketch, which is the minimum part. Hence, so if you have a bigger table, there would be less collisions, and you can increase the accuracy of the table. The question was, how do you make sure that it was actually already there? So the property of count min sketch, it will never give you 0 for what it has already seen. It would at least give you what it has, like some minimum amount. So going back to our original, the skew data problem, which is join. So then the steps for doing the sketch join would be, we calculate the count min sketch of the transactions, which was the larger data set. We add an integer column to the transaction, and based on the count, we kind of like randomly distribute. The integer numbers. We based on the count min sketch value of the key, again in the countries column, we replicate some of the entries. And finally, we do the join of transaction and countries with the country code and also the integer we had added as a combined join key. So, and then we get the unskewed data. So obviously, there's some overheads and limitations to this method. We have an overhead of doing a sketch calculation. And we are also replicating some of the entries in the smaller data set. So sometimes we might end up with a larger data to shuffle in the job. And also, this particular method would not work if, say, both sides are skewed. This would only work when one side is skewed, which you can kind of like get the counts from, and the other side has to be constant, so we know exactly how many times to replicate. You can do further optimizations with this. You can pre-compute the count min sketches beforehand for some of the commonly used data sets, and you can use them again and again for your jobs. Or instead of count min sketch, you can use another algorithm. You can get the top K heavy hitter keys from the big data set. You can probably join them separately using a broadcast join where it does not do a shuffle, where it does not move data as much, and you do the normal join separately. So that is it about skew data and sketch joins. Any questions? Okay. Oh, yes. I can talk offline too, or otherwise another explanation if I go back. So I'll talk about this table specifically. So here I've chosen a very simplistically like 3x4 quadrant. Obviously, I can say take a larger, say 8 hash algorithms or some 1 million rows or something like that to kind of like, so that collisions are not there. So in this, when I say I'm using hashing function 1, so US probably returned 1. The result of the hashing function was 1. So I incremented the value here. So whenever it would encounter the key, it would increase the value over there, right? So for US, it incremented over here, it incremented here, and it incremented here. So this is how it's actually incrementing the value. So for, again, if you see there's some degree of collision, which is like, say, Singapore, it actually mapped to the same 2 here. So which is why the count got incremented here as well. So the basis of the algorithm is when we want to like retrieve again, we hash them again with the same hashing functions, and we get the corresponding value. So this kind of like the minimum value would kind of imply that we have seen at least that key that many number of times. Oh, this is just to get the counts. This is just to get the counts. This is basically a replacement of that, which is the count of that. Oh, this does not deal with money yet. The transactions table, it comes like later on. This is just to actually calculate the count, which is just to get those numbers. Like it's just to actually get these numbers. Like how do I populate these numbers? We can talk offline more. Yeah.
So we have time for 2 more questions for any of the speakers.
I have a question to Elaine. Yes. So I'm trying to understand the jobs like better. So in mind there's basically like I'm wondering like how do you define jobs? Like do you just use the output of your custom model, or why don't you just look at event level data rather than user level data?
What do you mean by event level data?
Like for example, like the job like you describe is to say what does this user do with your product?
Yes.
And why couldn't we get this sort of information from event level data, like logging like the user what they did after the event?
Okay, so the question is why can't we get the jobs from the event level data? Why do we have to do the cluster? The answer is there can be like many events that users do on this product. So we're using clusters to find what are the like different things users are trying to do by like clustering the event almost. Yes. Yes, so we have this correlation of jobs versus margin. Yes, and we're also deriving like which job is the main contributor to the margin, so we can focus on the selling. What do you mean by job? I don't think we drop any features. It's more like prioritization of the features. All the features are important. Oh my god. We haven't done that yet, but I'm happy to hear more about like what you have done.
Okay, so all of the speakers will be happy to take more questions offline. We'll be hanging around for another probably an hour or so. I would like to close today's talk by first of all thanking all of the guests for coming tonight. I know you all have busy schedules and you took time to come here to hear our talks. Maybe it was the snacks, but I'd like to think that it was the talks. And I would like to thank all of our speakers and also our amazing events team who work very hard to make events like tonight possible. Can we give them a round of applause to our events team? They're in the back? Okay. And I would like to talk very briefly about communities at Stripe. So at Stripe, we value our communities a lot, and we have, as Ethan mentioned, some employee relations group. We also call them communities. So currently we have 9, and one of them, which I'm the active member of, is called Women Bees in Tech. So that's women and non-binary people who are in technical roles. And we do a lot of very cool things. We have monthly lunches. We have something we call small circles where people from different teams meet on a regular basis to talk in a safe space about anything they want. We also do a lot of brown bag lunch events with internal, very successful leaders and with externals, very successful leaders as well. And we, of course, do events like tonight where we have technical talks. So the whole idea is basically to build a community where we can learn from each other, where we can give each other advice, and we can support each other. So I encourage all of you to speak to at least 3 people tonight who you haven't met before and add them on LinkedIn. And at least with one of that people, meet for coffee or lunch before September 1st. Now, why September 1st? There is no reason. I'm just making this up so that you have some pressure and don't delay it until infinity. So with that, I would like to close it off, and please join us at the bar. Thank you.